Okay, so thank you for coming. So before I begin with my compile time errors, I'll start with the usual disclaimer that opinions are my own. But since I recently became self-employed, they're also my employers. And since I really like teaching, I would be happy to do it anywhere, anytime. If you or especially your company are interested in the sort of things I'm talking about here now or whatever else, I'm available here. I'll show a link at the end as well. Feel free to reach out and whatever. Okay, so start with a bit of dark history. So somewhere, sometime, someone was too smart for their own good and tried to encode something complicated at the type level. And we all know it when it happens. We see this kind of weird types trying to encode something complicated about, in this case, a database schema. And we'll get to the details of what I'm trying to do here later on, but someone was too smart for their own good. And then usually when we're doing something complicated in Scala with types, especially in Scala 2, implicits are quick to follow. And then you do something that you kind of offload all the heavy-duty type-level computation to implicit resolution in some way or another. And then when you actually try to apply this to something, to a specific concrete example, you might get burned in the following way. This is your error message. Something went wrong. An implicit was not found. What, where, there are like 4 or 5 different rules there. Which rule failed? What field wasn't appropriate? What happened there? Nothing. That's what you get. If you're lucky, maybe you have an implicit stack trace, but then if your logic is sufficiently complicated, it's really, really difficult to debug or decrypt in any way. My claim is here that in Scala 3, these days, we can do better and a lot better. So for this talk, I'm going to introduce the compileTime.error function, which is a new addition in Scala 3, a few years ago, new. And first glance, it might seem quite simple kind of function without any interesting repercussions. But actually, we'll see that by leveraging some of the new type-level programming features in Scala 3, we can, and we'll review those features as we go along, we can actually leverage this function to develop and create developer-friendly custom errors at compile time that will also solve the problem I just described on the previous slide. So. And I'm going to be guided by a realistic example, so the schema validation thing would be our guiding example. I won't be using any macros at all, so you could claim that even in Scala 2, you could somehow solve this problem with a custom macro one way or another, but the techniques I'm going to show you here are more general than a specific macro that you tailor for your specific problem, and so everything you learn here will be applicable maybe in other contexts as well. So I think learning these techniques is more useful than trying to wrangle some macros. And also because of time constraints, this is not a tutorial, so I'll be skipping many details, but you can see the full code and all the details in a repo that I will link to later on. So the issue that we just saw before was an issue of poor error reporting, and so this is what we want to solve here. But let's first introduce the actual problem that we're trying to solve. So we want to have a class representing a database schema, but the DBAs in our firm, they have very strict requirements about what can go into a database. Specifically, we can have and those may seem arbitrary, but you don't argue with DBAs, so that's the law. So we can have at most 25 fields, exactly one key field, exactly one timestamp field. Strings cannot exceed 500 characters, and for some mysterious legacy reason that nobody can trace back, all fields must have the prefix TR. Why? No idea. And it's been a while since I actually met DBAs face to face, but I kind of imagined them like this. And I really don't want to get on the wrong side, so I really prefer to enforce all these rules at compile time so they don't accidentally leak to these guys and hunt me later. And so to make this problem more concrete, here's the class that we're going to be using as a model. So we're trying to model hotel data in a database. And we can see that, and there are many more fields here as well. We can see that some type safety is being enforced using more sophisticated types, like for example the size string here. We're trying to enforce the size of the string directly in the type. But the requirements that I just spelled out are quite more sophisticated than can be expressed in a simple type. And so to implement those different requirements, we'll have to do something more sophisticated than just putting type annotations directly on our class. Okay, so let's first introduce the star of this talk, the error function. So here's a very simple usage of this function. So you start by importing the Scala compile time package, and not sys error, the compile time error, and then you can, in the REPL, do an error with a custom string, and you run it, and that's what you get. And it's important to understand that this code failed to compile. Nothing is actually executed. You got your custom error directly at compile time. So this is the basic premise of using the error function. Sorry. And so with these humble beginnings, we can actually start implementing something more sophisticated. So let's start by implementing the first requirement that I described earlier. So we want to make sure that the size of the case class is not larger than some specified limit. So this is the signature we're going to use. We're going to check some type A, presumably a case class. We're going to have a certain max size, which is given to us as a parameter, and we're going to require an implicit or given case class instance, which I will describe later in more detail, but essentially it's all the compile time information that we know about the case class at compile time. And so here's the implementation. So in this case, we're checking whether the size of the case class is larger than the limit. If it is, we're producing the compile time error. So, but it's important to note here that we're using an inline if. This means that this snippet of code will be evaluated by the compiler at compile time. And so it's important that all of the involved moving parts are actually compile time constants that the compiler can evaluate. For example, if you try to pass a variable here which is not known at compile time, the compiler will complain that it wasn't able to evaluate the inline if. But if you actually try to use it and compile it, it works as expected. So you check the size of the data table and see that it is indeed larger than 20, and so we get a compile time error, which is exactly what we wanted. So that's a step in the right direction, but this error message is not as friendly as we might expect it to be, because it doesn't tell us anything about what was the expected size and what was the actual size of the class that we tried to check. And so since we're striving for developer-friendly messages, we'll try to get all the possible information that we have directly into the error message. So here's a second take. Sorry. So here we're doing the same thing as before, but now we're also adding information about the size of the class and the expected, the maximum size that we're expected to observe. And so we can try to compile that, and we get a compilation error. But unlike last time, this is not the right compilation error. It's not failing to compile because the class is not the right size, but it's failing to compile because the call to error was not correct. It tells us that you cannot use a non-literal string as an argument to error. And that actually makes sense, because the error function is being evaluated at compile time, and so it cannot just, unlike macros that can have lots of flexibility in evaluation during compile time, the error function is actually quite limited to basically evaluating just compile time strings, compile time known strings. And so in this case, transforming an integer into a string at compile time is something that's not supported with the error function. So actually, let's see the rules of engagement, so to speak, in more detail. So, so what the error function can evaluate is compile time constant strings, and they may be separated by the plus operator on strings directly. So that means that this first piece of code is okay. You can concatenate strings, and it's okay. But the second one won't work because it cannot evaluate any of the functions, and it can't also use the plus with an integer because it's not the same plus as string plus, and it also can't use string interpolation because it's yet another function that's not supported at compile time. So, so this seems very, very limiting because we want to put in as much information as possible, but we're very limited in what sort of info can be actually used at compile time as a string. So where do we actually get compile time constants? So as before, we saw the string literals. We can just write a literal string. The compiler knows about it, and that's okay. We can also use inline literals, which is a new capability of Scala 3, which will allow you to inline the same literals at compile time at the invocation site. And given the fact that inlines can be recursive as well, you actually can get quite a lot of mileage from just using inlines in recursion. But it's still quite limited for reasons I won't actually get into here. And the third option is the one we'll actually use, is the const value function. The const value function takes a type a compile-time literal type or singleton type and converts it into a compile-time constant that matches that type. So for example, we have the type message, which is a string literal type, not a value. We also have the integer literal value 1 to 3, and a compile-time function, a type function from integers to strings. And both of those are types, and we can pass them into a constant value function and get back a value, not a type, that match those types that we had at compile time. And this is, and since constant value actually produces compile time constants, we can actually pass them directly into the error function. That will be our gate to be able to implement something more sophisticated than what we had before, because type level programming in Scala 3 is actually very sophisticated, and you can do a lot of things just by doing things like toString at compile time. So let's see a reimplementation of the previous function. So here's the new signature. In this case, we're now getting max size as a type input, not as a value argument. And we do the same comparison as before, but instead of using values, we're using types. So we're taking the size type from the case class and the max size type that we got before. And we use constant value to drop them back into a value, and then this can be evaluated at compile time and do the check. And in case the if failed, then the if succeeded, then we can produce an error message, which is a bit noisy because we can't use string interpolation. But basically, we're taking these arguments, convert them to a string using the built-in toString type function, and then pass it through constant value in a way that's appropriate for the error function at compile time. And it's quite roundabout, but it actually works. This is a very nice error message. It tells us exactly what went wrong and gives us all the information we need. So this is, again, a step in the right direction. And though it is a shame that we can't use string interpolation, but still. So to conclude this part, so the error function is quite useful for simple static errors. But as we just saw, this limitation of using only compile time constants is very, very limiting, unless we want to take it to the next level and use the type level computation at compile time to provide more interesting types and string literals to the error function. And what we saw here just a slide ago is just a hint of what we can actually achieve. So for the next step, let's dive deeper into type level programming in Scala 3. So this is going to be a very quick review of the capabilities of Scala 3 at the type level. So there are many type level features in the Scala language, and you can just go about them on and on and on and on, and there are very many of them. The list is kind of endless. And it may feel overwhelming with all these features, how you can actually do something, how do you solve specific concrete tasks. And it's a whole subject unto itself, but to make it more concrete, what is important is that these features kind of form a small language that we can use in Scala at the type level, and this language is actually quite nice and useful. And to illustrate the point, I'll just use a concrete example where we use this small language, and hopefully we'll gain enough intuition so that we can implement our requirements for developer-friendly errors. So I'll start by some simple value level code, and we'll translate it gradually into the type level. So suppose you have a list of values and a naive implementation of the map function, which does pattern matching and recursion. Don't put it to production, please. It's not a good implementation. Then we have a couple of transformations using higher order functions and anonymous functions to actually perform the transformations. And we fold the final result by just going over the different parts and converting them to a string. So this is kind of fairly simple Scala value level code, nothing that should be too surprising for Scala developers. The thing is that we can actually transform it to type level by going quite mechanically and just applying some very simple rules. So first of all the defs are becoming type declarations. And since by convention types are uppercase, then we do the same uppercasing. Next, lists become tuples in Scala, and this is the syntax for arbitrary sized tuples in Scala 3. So it's very similar to linked lists. But notice here that this is no longer values. These are types. These are the literal types 1, 2, 3, and 4, not the values. And we have a tuple with four elements here. Next, what we were doing here is converting the map function. Instead of taking arguments as a list and a function, we're taking lists become tuple and functions become type constructors, because a type constructor can be thought of as a function from type to type. Next, because types in Scala now support match types, we can convert the pattern matching directly, pretty much one-to-one with the original implementation. We just match on the type. In case it's empty, we do one thing. In case it's not empty, we apply it to the head and go recursively to the tail. So this is a fairly mechanical transformation. Next, we can transform the numbers that we had before. So here we're using the fact that we can use type constructors in infix form. And this little weird arrow is the way to apply a type lambda. So this is the equivalent of an anonymous function at the type level. So it takes a type and produces a new type. And here we're also using the built-in type level functions in the Scala compiler to do addition and comparison on integer types in a way that's very similar to the value level. And the last part is to do the fold. So the fold pretty much a mechanical translation. So we use again the toString function, and we use string concatenation at the type level. And we can actually evaluate it in a sense by just taking this result to the const value, and we get a string back. And this string, something that we computed with more sophisticated steps, with non-trivial logic, this string can be used in the error function. So this is our gateway to shoving complex logic directly into the error function at compile time. So this is our type level language. We have tuples instead of lists. We have pattern matching and recursion and an equivalent of anonymous functions. So all the ingredients you need for a simple functional language, something that most Scala developers are well familiar with. It does tend to be a bit loosely typed. We'll see many usages of just raw tuples when we actually use it. And so in a sense, Scala, the type level is a dynamic language, which sounds strange, but whatever. But and it's also a shame that the language doesn't support string interpolation, just like Scala back in the day. And hopefully someone will come up with SIP11 at the type level so we can get nice string interpolation. And like many things in the Scala language, it's quirky but serviceable. Like there are some rough edges. This language doesn't work exactly as expected all the time, but it works, and it will work well enough for this use case. How many people know this movie, Spinal Tap? Not that many, okay. It's a fun movie. Anyways, so now that the groundwork is laid down, we can actually turn it up to 11, so take it to the next level and actually use all these techniques to produce those developer-friendly error messages that I keep talking about. At least promising. So before we can actually produce error messages, let's take a look at the inputs that we're going to use. So previously I mentioned the case class type. So let's see what it's made of. So this is the case class type for the hotel table, and we can see that it contains types that describe the whole structure of the case class that we provided it. So we have a long tuple full with field descriptors with all the info that we need about this type. We also have the name as a type. And if you're familiar with the mirror type in Scala deriving, it's basically the same thing, just slightly repurposed in a way that's more convenient for this use case. And so because all we have here is basically a tuple with field descriptors, it means that in order to be able to produce nice errors, what we'll have to do is to do some type level programming over these tuples at compile time. Okay, so the powers that we just revealed in the last section, where we can program over tuples at compile time, will be used here to kind of go over these fields and convert them into useful errors. So we'll start with a small framework for compile time checks. I know people love frameworks, so this is it, a compile time one. So the first ingredient is the check type. So the check type, what it does is just to wrap around the function from tuples to something. Notice that I'm not constraining the input or the output in any significant way, because it's possible, but probably will be quite daunting to do it at the current level of the type level language. So then next we have two helpers that let us provide messages, error messages. So one takes a message, which is a string, and turns it into a singleton tuple, and the other says that everything is okay, and it's an empty tuple with no errors at all. The reason I'm using tuples and not something like an option is because we're going to be accumulating errors into a single list. So I'm kind of cheating and abusing tuples for this purpose. If you were to actually implement this framework for a real thing, maybe you'll do something more civilized. Next, we're kind of aiming for a DSL kind of feel, like a domain-specific language for errors at compile time. So I'm having a function that takes a Boolean condition and an error message, and if the condition is not met, then the error message is produced. So either OK or an error with this error message. And the last ingredient for now is that we want to apply checks. So basically, we're just trying to extract the check from the check wrapper. So we take all the fields, the tuple of fields that we saw before as an argument and a check, and then we just extract the check and apply it. We'll see later on how we actually use it. And if you want to think about it in value level terms, this is kind of a type level equivalent of validation with non-empty list of strings as the errors and the unit as an output, because I don't have any useful output as here. But just like validation, which is important here, we're going to be accumulating errors. So we're striving for developer friendliness, so we don't want to expose one error at a time and then force the user to recompile, then again and again. We want to take all the errors into a single list, which is exactly what these helpers are helping us do. So we can start implementing our requirements now at the type level completely with this little framework that we just defined. So here's the equivalent of a signature that we're going to use. So we have a max size type input, and we're going to implement a check that takes fields, a tuple of all the fields as an input, and then we can create a check. So this is, I find it kind of readable. So we take the size of the field, so the size of the tuple, compare it to max size. This is a built-in operator that Scala provides us with to compare number types at compile time. And then if it fails, we have this error message, which, although lacking string interpolation, which is kind of annoying, but is still very informative and quite readable, I think, if you get used to all the noise around. So we can actually even run, in the sense, we can run this check in a way. So this is, so here we summon the case class for the hotel table, and then we create two types, apply the check on the fields of our case class. And we check it once with 30, once with 20, and here it succeeds, no error messages, and here it failed with a very informative message that we'll be able to show the user later on. Now I'll have to speed up because I don't have any time, I'm sorry. Okay, so it wasn't that bad, hopefully. So the syntax is a bit foreign, so it's like a different language, not really Scala, but still it's functional. Before we would have to use kind of a prologue kind of thing, which might feel alien. Here I think it's nicer. So let's quickly implement the second condition is exactly once. We want to make sure that a certain type appears exactly once inside our case class. Due to the limitation of what's available in Scala right now, I can't get the type name as a string using anything built in, so I have to pass it as an argument as well. But next we collect all the fields of this type. I'll show the function in a moment. And then if this collection of this tuple of all the fields that has this type is empty, then we have an error. So in this case, the field is the type is missing from our case class. In case we have exactly one instance of this type, we produce OK, which is correct. And then the last case, which is a bit noisy, and I hope someone comes up with a string interpolation at the type level compiler plugin or something. But basically it says, okay, we have more than one instance of this field, so we produce a message that contains all the relevant information about this thing, including the size of how many times I saw it. And also there's a helper function that renders all the offending fields with this type. And here are the helpers. So collecting the field types is just a filter over the fields where you extract the type and check whether it's a subtype. And rendering is just mkstring, just like collection mkstring, but at the type level, applied to the field names that we just got. And so the specific checks that we need to apply is for key and timestamp. Unfortunately, I have to duplicate their name as a string, but that's one small limitation. But these are the checks that we have to implement. So 3 down, 2 more to go, and like 6 minutes. So let's see whether we can turn it up to 11. Okay, so the next 2 checks that we have are per field. So each check should be applied to every field independently. So we'll lay down a bit more groundwork for this. So here's a function that, type level function, that checks all the fields. It takes a per field check and it creates a new check that takes all the fields and then applies this check to each field separately and then uses flatmap to concatenate all the error messages into a single long list of errors. Apply to field is the function that takes the field, applies the check to it, and then renders the field. If there's an error, it renders the field name directly in the error message. So we're prepending the field name into the error message so that the users can know exactly what field failed. So we're really going for the kind of developer friendliness points here. But now we can actually use this little helper to create another check. So we want to check that all the strings that we have in our case class are bounded up to a certain limit. So it's very similar to the check we did before with the class size. So we get a max size input as before, but now we check each field independently. And so given a single field, what we do is we get the field's type. If it's a size string of n, then we check that size, and if not, we fail appropriately. If it's a raw string, we forbid it completely because we don't want to have any unbounded strings. Otherwise, we say it's okay and move on. So this is this check. And the last one is the prefixes. So we have some legacy reason that we have to enforce a prefix on the field name of every field in the schema class. So in this case, what we do again is a pair check field. We use the built-in function matches. So matches takes a string type and a string and a string regex type again, and checks whether there is a match. This is a built-in function. We won't be able to implement it ourselves easily, and that's part of the limitation of working at the type level like this, because whatever the compiler provides for us is pretty much the upper limit of what we can do. In many cases, for example, I couldn't get the type name from the type itself without writing it down manually. So it will be very nice to have like an extensible mechanism for type level functions that's currently not present, but otherwise it's kind of straightforward. So we have the prefix, make a regex, and if it doesn't match the field name, then we're saying that the field is missing the prefix, and again we're being friendly and we're putting in the actual prefix that's missing. And that's it. These are all the checks that we want to implement, and we want to aggregate them into a single kind of descriptor of all the rules that we have to follow. So we'll do it as a tuple of checks. So no checks is an empty tuple, and now we can now add that we have at most 25 fields. We have exactly one key and exactly one timestamp. We have string fields that are at most at 500, and we have all fields have the prefix tr. So it's very similar to the code that we had before with the implicits, but now written in this new kind of type level language that we just defined. And the question is whether it will work just as badly as before, or whether we kind of managed to improve in a way. So we have to run those checks, and before we can run them, we'll put the last building blocks of our little framework. So we're going to create a runner that takes all the checks and applies them, and then concatenates the results with flatmap. We also have rendering for the error, so we want to be friendly, so we say some checks failed, the type name, some new lines, and then we take the list of errors and combine them, concatenate them into a single list with new lines. And to give an extra flourish, we itemize by using prefixing with a dash, just so that the users have a feel of kind of a serious thing from the compiler and not just a custom-made error function. So finally, we're ready to come back to the error function. So we want to actually perform the checks. So here's the final function that will do that. It takes a tuple of checks and the type, and the case class instance for that type. It then applies all the checks to the fields of the case class. Notice that we're now tying the type level computations back to the value level. We're again we're now doing a value level thing with the type level check that we just defined. So now we have a type of errors. And now if this type errors is empty, doesn't have any errors, then we're done. The compilation can proceed. But if not, we want to show the errors to the user. So the question is, how do we actually pattern match? How do we actually take these values and pattern match on them at the value level? And for this purpose, Scala has a special function, magic function called erased value, that takes the type and produces a dummy value that you can pattern match on. So it's a dummy value, so you can only match on its type, but not on its value. But it's not for us, so we can say, okay, in case the type of errors is empty, then we're done, it's okay. If not, we're going to take the errors, render them with the class's name, and apply it to const value, and then back to errors. Now we have a constant string at compile time, which describes all the errors that we had during the application of these checks, and it all can be used directly in error without any limitations. So that's it. We're done, basically. And now is the moment of truth. Does it actually work? It will be embarrassing if not, I guess. So here's, we're doing perform checks with the schema checks over a hotel table, and nothing happened. Right, so hotel table is actually a valid schema, so it should compile, it's fine, everything is okay. Now the real moment of truth, here's another one. So we have the suspiciously named bed hotel table, which we try to check again. Do you feel the tension, anyone? No? Is it going to work? Look at this. Isn't this amazing? We have like an error, many errors, and they're very descriptive, and you can see like which fields failed, and have like numbers and stuff. And do you ever see such nice errors in like implicits in Scala, ever? So we can easily see what failed and what fields exactly, and we can debug it, and it's very nice. Even the DBAs are happy now. And if they're happy, we are truly done. So, to conclude. So we saw that despite the humble name, the error function is quite powerful. You can start simple with fixed strings, but you can really go all the way up to 11, just like we did a moment ago. By harnessing the functional language at the type level, making compile time capabilities is almost endless. So you can apply this language and do pretty much anything you want, limited a bit, but still you can do very impressive things at the type level. And with just about 100 lines of code that I just showed you, I find the code actually fairly readable once you get used to this weird little style. I actually was quite surprised myself that this worked out so nicely. It wasn't obvious to me that it will work at all. So custom compile time errors is now something that any developer, I think, can craft. And what's better than delighting your fellow developers with beautiful, developer-friendly errors, and all the while enforcing, notice that we enforced complex invariants using complex invariants where they belong at compile time. So we didn't let anything leak into the runtime at all. And this is, I think, some very exciting kind of uncharted territory in Scala. And like any uncharted territory, there are kind of rough edges and things don't exactly work, like metals will go crazy and the Scala REPL sometimes just fails on it I don't know, but still I think it is exciting. And I hope this talk inspires you to kind of look at Scala's type level capabilities and see what you can do with them on your own, with the error function and without it. But the error function really ties it back to the user in a very friendly manner. And so this is the full presentation. You can see there if you want to contact me with anything, especially if you want me to teach like workshops and stuff, and I'll try to talk slower next time. You can reach me out here. Thank you.